On this part of physics, we are going to talk mainly about thermal energy. And we'll go into many points, like what's the difference between temperature and thermal energy, and how thermal energy is transferred from object to another, and what is a specific heat, and also melting or fusion, vaporization, or latent heat related, plus the entropy and first law of thermodynamics. Okay, if we go to the first point now, what's the difference between temperature and thermal energy? We have temperature and you have what? Thermal energy. Okay, temperature now, we all use, and we know that temperature, it means it's a measure of how hot objects are. How hot objects are, whether is it air inside a room or a person or any other object. So temperature, it depends mainly on the average of kinetic energy of the particles inside an object. How does that happen? So for example, if I have this object, and inside this object, as we know, it has molecules. These molecules, that means atoms in a specific ratio. This object now, when we heat it, what will happen inside this object? These objects, as we know, the electrons and molecules are in general in random movement. So when they are moving particles, that means they have kinetic energy. Okay, if we add heat now to this object, if we heat it, what will happen? These objects, they will move faster. When they move faster between themselves, that means they have higher kinetic energy. So that means when you add to it heat, that means you are adding energy as heat. This heat now will be transformed into different types of heat inside the object. So it will be changed into a moving energy, which is kinetic energy. Now, when you go to measure the temperature of this object, the temperature, when it tells us that the temperature of this object is 35 Celsius or 25 Kelvin or whatever. So what does that number mean? Or what does it measure? It measures exactly the average of the kinetic energy of these particles. So does temperature depend on the amount or the number of particles? No, because it depends on the average of their kinetic energy, whether they are 3 particles or 8 or millions or billions. However, so it doesn't depend on the number of particles, but it depends on the average of their kinetic energy. So it depends on the average kinetic energy of the particles inside the object, not the object itself, but its particles. And what is the units that we use for temperature? We use Celsius, and we use what? Kelvin and Fahrenheit. In general, we use these ones. And Celsius is a scale of temperature that was created based on water. Based on what? On water. So that means it was made by making 0 Celsius as a measure of water when it is at the melting point. So that means melting point, that means when the water is changing from solid into liquid, that temperature we make it what? 0 Celsius. Then when water evaporates, that means when water starts to change into vapor, that means to be changed from liquid into gas, at that point the temperature is what? Is 100 Celsius. So 0 Celsius is the freezing point of water, and 100 Celsius is the boiling point of water. So and this is the range now, and it was created based on water in this case, while this one it was Kelvin based on absolute value. That means when gases has the least kinetic energy. Okay, related now to thermal energy. What is thermal energy? Thermal energy is the total, it measures the total amount of kinetic energy of the particles of an object. So that means this object now that it has many particles inside it and they are moving, so they have kinetic energy. So the total amount of kinetic energy of all these particles is called what? Thermal energy. And its unit is joules because it is energy. And it can be as heat, and it is also what, when it is transferred, it's called heat. But so thermal energy is the total amount. So when I say the total amount of kinetic energy, that means how many particles is important. So that means if there are two particles, it's not like 1 million particles because each one has kinetic energy. So when we add them, so that means their number, it matters here. So that means thermal energy now, number of particles in an object. When the number of particles in an object increases, so that means thermal energy increases. But it's not there here the same for temperature. It doesn't mean when number of particles increases, temperature will increases. No, only for thermal energy, because here it depends on the total kinetic energy of all the particles, but here it's only for the average. And the average is not related to how many particles are there. Okay, now, thermal energy, it can be transferred from an object to another, and it has types of transferring. We're going to study it now, just next point. But here we need to add now thermal energy. What do we use to measure it? We use in general like thermometers, but here we use what? Calorimeter. Calorimeter is a device that tells us how many calories, that means how many joules an object has, so that means thermal energy. Okay, move now to the second point. What is the second point here? As we know, thermal energy, it can be transferred from an object into another, These objects now are different. So for example, if I have solids now, and here I have gas and liquids, and here I have what? Vacuums. In solids, heat is transferred from a solid object to another solid object by only conduction. What does that mean? That means these objects, they have to be in contact with each other, so that heat is transferring from one object into the other object. So when heat now is it transfers from a higher temperature object to lower temperature object. And the heat will continue moving, transferred from hot object to cold object till they become at thermal equilibrium. What is thermal equilibrium? When there is no difference between the temperature of these two objects. So in this case, we say these two objects are in thermal equilibrium. So on solids, they have to be in contact so that energy as heat can be transferred from hot or higher temperature object to lower temperature object. Okay, related to gases and liquids, do they need to be in contact? Okay, if a person now is cooking now in a kitchen of your apartment or your home, and you are in your bedroom, by the way, you're gonna smell. And you may estimate or predict the type of food that they are cooking. How do you smell that? What came to your room? So that means when they are cooking here, when they cook on the kitchen, by the way, the parts of your food, parts of the food will go into the air as small molecules of the food itself. It'll be transferred like gas. So these ones now, as gas, they go by diffusion into what? Into the air, and they move, then they come into your place. So you smell that food because these particles move. So that means now, in conduction, we need contact between the object to transfer heat. But here now in gases and liquids, here is the same. The particles themselves, they move from a place to another place. So they transfer the energy by their movement because they move. But here, here they don't move. This solid object remains in its place and this one remains in its place. And only the heat, because of conduction between, because they are on contact between each other, so heat transfer from one object to another. But here now for gases and liquid, as we said, the particles, they move by themselves. So they move from one area to another area. So that means if you heat, for example, now this one now is a container of water. If you heat it now, these particles, they will be what? Heated, they will be hot. So by themselves, they move up. They move up. And these ones, they move what? Down. So this type of movement now, we call it convection. We call it what? Convection. So that means transferring of heat in gases and liquids is called convection, and it is due to the movement of the particles themselves, the hot particles moving. Okay, one example of, real example of convection here. Have you asked yourself why in your room we put air conditioners up? Air conditioners, we put them up. Usually, air conditioners are fixed or placed on the upper part of the room. But heaters in general, we put them down. We put them where? On the ground. Why don't we make the opposite? Why don't we put usually heaters up and air conditioners down? Why? I think some of you asked them yourselves before about that. Anyway, air conditioners now, they give you, they make the particles around them here colder. When these particles of air now becomes colder, their density becomes greater. So that means they become more denser or denser than the other objects. So when the particles have more density, they usually go down. They usually go down. And on the other hand now, these particles that were here, they become hotter than these particles that they went down. So they start going what? Up. So they go up to the environment around the air conditioner. Then they are called to be what? Cold. Then they have higher density than the particles that they are here. So in this case, they go down. So that means you feel like the room, it is in continuous movement of the particles up and down, while the air conditioner is up. Same thing for heater. So heater now, it will heat the particles around it. So these ones now, when they become hot, they'll have less density. So when they have less density, they'll go up. Then objects with higher density will go down. Then they are heated and they move up like this. So that means that's why we put air conditioners up, because we need it to make the particles up cold. So these cold then particles, they'll go down by themselves. And the same for heater. We needed to heat the particles that are on the ground, and usually they have higher density. So when we heat them to get less density, so they go up. So this now type of transferring of heat is called what? Convection, and it happens in liquids and gases, or what we call it what? Fluids. So you have now two types of heat transfer. We have conduction and we have what? Convection. What is the third type of heat transfer? It happens in vacuums. So what's the difference between here and here? Here we should have mediums for heat to transfer. So that means from object to object, they have to be in contact. And here now, also they have to move from place to another place for this here. But for vacuums, for example, from the sun here, and this is the earth, when the sun sends its rays, electromagnetic rays, including heat, how it reaches the earth, and there is no particles here in the universe, no particles here. So that means this is what you call it what? Radiation. So radiation is the third type of heat transfers, and it happens when there is no medium between the two objects. So between the earth and the sun, there is no medium. So radiation now sends heat as electromagnetic waves to the earth with no need for the medium. So we understand now the three types of heat transfer, and we understand each one, where is it. Here conduction, as we said, it is in solids, and also it is faster in metals. So if you have a metal here and you heat part of it here, directly you will feel the high temperature here, because now transferring of energy, of kinetic energy between the particles, because they are tightly packed, so that means they can transfer the heat between themselves faster than other objects. Okay, we go to next point, which is specific heat. What is now specific heat? If I have here 1 kilogram of water, and I have here 1 kilogram of iron, for example. If both of them, their temperature is 20 Celsius, both of them 20 what? Celsius. Okay, if we want to increase now, if we want to increase this 1 kilogram and this one is 1 kilogram, if we want to increase now the temperature of water and iron by 1 Celsius, by only 1 Celsius, what do we need to do? What do we need to do? We need to add heat. So that means we need to heat these ones now. When we heat these two pieces or these two objects now, when we heat them, that means we are giving them energy. And this energy will increase the kinetic energy of the particles inside. So their temperature will be increased, because it's a measure of the average of kinetic energy of the particles. So now, when we give it heat now, the amount of heat is measured by using the joules unit. So that means now we can count how many joules we can give each one of them to raise its temperature by only 1 degree. So now the question, which one now we give it more heat to increase its temperature by 1 unit, by 1 Celsius here? Is it the kilogram of water or the kilogram of iron? So of course, for water, we need to give it more or much more heat than the heat given for iron. And this amount of heat now that is given for 1 kilogram of a substance to increase its temperature by 1 degree is called the specific heat. So in this case now, specific heat of water is greater than the specific heat of what? Of iron. And water in general, it has one of the highest specific heat of all other materials. So specific heat now again is the amount of heat that is given for 1 unit of mass. In this case, it's going to be 1 kilogram, to increase its temperature by what? By 1 degree. Okay, if we can change this definition as equation, we can see that the specific heat equals the quantity of heat that is given for what? That is given for 1 kilogram of a substance. That means to the mass. Then to increase its temperature by what? By 1 degree. So that means this is the change of what? Of temperature. So that means this is now the formula of a specific heat, and it's the same like the definition. Quantity of heat that's given for this one. Now we needed to make it 1, and here we needed to make it 1. Why? Because we need to make the denominator 1 to make the definition right. So that means quantity of heat that is given for 1 unit of mass to increase its temperature by 1 unit. Whether is it Celsius or Kelvin, it's the same in this question. So specific heat, no problem what you use, either Celsius or Kelvin. And it depends usually on the question, because now we deal with the change in temperature, and the change in temperature, whether is it in Kelvin or in Celsius, it's gonna be the same change and the same number. So that means the number here will not be changed. It will remain as it is. Okay, you understand now what is a specific heat, and you understand its formula, and what is its also what? Unit. So the unit will be, the unit here of quantity of heat is joule, and here it's going to be kilogram, and here it's going to be Celsius or what? Or Kelvin. Either Celsius or Kelvin, both right here, and it depends on the question what it gives you. If it gives you the unit of the specific heat Celsius, use it Celsius. If it is Kelvin, use it what? Kelvin. So you understand now specific heat. Okay, if we say another idea for a specific heat. For example, I have a material X. That its specific heat is 400. 400, what's unit? Joule for each kilogram times Celsius. Okay, in this question now, again, what does the 400 mean here? It means we need 400 joules. We need 400 joules as energy to increase the temperature of 1 kilogram of the substance by 1 Celsius. By 1 Celsius. Okay, if we give this substance only 100 joule, 100 joule of energy, what will happen? What this energy will be able, what it can be able to what? So since this 100 is quarter of the 400, so that means this 100 now will be able now to increase quarter of the mass. That means quarter 1 kilogram. So that means it will be able to increase quarter of the kilogram of mass here of this material, 1 Celsius. This is one idea. So that means it's gonna be able to increase the temperature of quarter a kilogram by 1 Celsius, or it's gonna be also able to increase 1 kilogram of a substance, but here just by a quarter degree of Celsius. Is that clear? So you understand now a specific heat and its formula. Then we're gonna solve questions related to, you have here 4 variables. On the question, in general, they'll give you 3 variables, then you find the 4th one as math. Okay, for next point now, we are going to talk about latent heat of fusion and latent heat of vaporization. Okay, fusion here. What is fusion and what is latent heat of fusion and latent heat of vaporization? If I have here ice. If we have here what? Ice. So this piece of ice now, we need to melt it. That means we need to change it into what? Into liquid. So we'll give it heat. When you give it heat now, and for example, this ice is 1 kilogram, is 1 kilogram. We give it heat, it's gonna be changed into what? Into liquid. But will it be changed once as liquid, or it will take time? It will take a little bit time. And it will start by some parts of the ice will be changed into liquid while the other part is still ice. Then it's going to be changed. And this process of changing from the starting point of a changing to the final point it changes when all the ice becomes liquid. This part we call it a phase of a change or fusion. We call it what? Fusion. And at this part of a change, temperature will not be changed. Temperature will remain 0 Celsius. 0 Celsius. So at the process or at the time of a changing or the phase of a changing, the material or the object is a change while its temperature remains the same. But it still needs heat. This heat now that we are giving now, it will be responsible for breaking the bonds between the molecules here in this case. So that means it will break these bonds while the temperature remains the same. Okay, the amount of heat that we give it here now, the amount of heat that we give it for this substance is called latent heat. Latent heat of what? Latent heat of fusion. Latent heat of fusion. So that means it's the amount of heat that is given for a substance to change its state from solid to liquid. It's called what? Latent heat of fusion. And latent heat of fusion, which is Q, it equals the mass of the object times heat of fusion. Constant. Here is specific heat of fusion. What is now this one here? Specific heat of fusion. It's the heat that is given for 1 kilogram. For 1 kilogram of a material to change it from solid into liquid. So that means if you give, if this one now is, for example, if this part is 5 by its with its unit joule per kilogram, per joule per kilogram, and the mass is 3. The mass is 3 kilograms. What will be the amount of latent heat here of fusion? You're gonna multiply the mass times the latent heat of fusion, and you'll have examples to apply that. Same thing for latent heat of vaporization. If I have here liquid and I want to change it into what? Into gas. I want to change it into gas. So that means we need to give it heat, and this amount of heat that is given for a material or a liquid material to change or to transform its state into gas is called latent heat of vaporization. And when here the material starts changing into gas till it finishes and all the particles are changed to be gas, at this process temperature will remain constant, which is 100 what? Celsius. While the heat needs more heat to be changed, and this amount of heat, we call it latent heat of vaporization. And latent heat of vaporization, it equals the mass of the material times the specific latent heat of vaporization. So that means when this one is given, just to multiply this one now, it means the heat that's given for 1 kilogram of a material to change its phase or its state from liquid into gas. So this one for 1 kilogram. And if you have 5 kilograms, 10 kilograms, that means you're going to multiply the mass by this number to get the total quantity of heat needed to change the material from liquid into gas. We'll move now to the next point, which is first law of thermodynamics. First law of thermodynamics. For example, now I have here an engine of a car or of any other vehicle or machines. So here now, this engine now, we always, to make it work, we give it energy. But what type of energy? It can be thermal energy, it can be mechanical energy, whatever is it. But if it is now here, we deal with it like thermal energy. When we give it thermal energy, and this engine will produce work. The work now here is going to be like mechanical work, like movement. It's mechanical, okay? So that means the energy that is given for this engine, and the engine just changes now the energy that is added, which is thermal energy in general, into what? Mechanical energy. And both energies are in joules, So if we give it now 100 joule, if we give it 100 joule of thermal energy, will this engine be able to give us 100 joule of mechanical energy or work? And this one is called work now. The work done, or the things, or that this engine will produce, or its task mainly, we call it work. So that means now will it be able to give us 100 joule of mechanical energy, 100 joule of work? In this case, the efficiency in the engine will be 100%, and that's almost impossible. So it will give us here about 90 joules of energy as mechanical energy. So this engine means, it takes 100 joule as input heat, and it gives you work like what? 90 joules. What will be the efficiency here of the engine? The output divided by the input. So 90 over 100 is going to be 90%. So this is what's the efficiency of engine means. Means what is the amount of work that this engine does based on the quantity of energy that is supplied to that engine. So if this one is 100 and it gives us 90, that means there is a loss. There is a loss of energy by 10 joules. Where did that 10 joule go? Where did it go? Mainly, this 10 joule of energy will be wasted energy, and this wasted energy will be consumed here to heat the particles of the engine itself. So the engine itself, while it works, it has particles. These particles, when they touch heat, they'll take part of this heat, and their kinetic energy will be higher. So that means the temperature of this engine will be increased. So the internal energy of this one here, or the latent thermal heat or thermal energy of this engine, will increase due to what? This one. So that means what will be the amount of internal energy changed? What will be the amount of internal energy change in this engine? It will equal the energy supplied minus the work done. So that means if you make 100 minus 90, you will get 10, and this 10 will be the amount of a change in the energy of the engine. And it works also with reservoirs. Sometimes here you have, for example, you have a system here. In some homes in cold areas, they take pipes. They use pipes inside the wall. And in these pipes of water, they water as vapor, it moves through it. That means hot, or high in thermal energy. And when it moves through the pipes, it gives, as long as it is in contact with the wall. So that means energy will be transferred from this steam, which is from water vapor, into what? The wall. So that means the wall of the room will be what? Hot. So that means this is type of heaters in some cold areas. So now this water or this steam, when it starts moving here, for example, the energy of it was 100 joule. When it goes back now here to hot reservoir, to cold reservoir, here, when it moved to the cold area here, the cold reservoir, it started from the hot reservoir, then it moved to the cold reservoir. So if it started by 10 or 100 joule, so it will lose here the energy, and this is the goal, to lose the energy to the wall, so the wall becomes warmer, and that's the goal. But when it comes back to the cold reservoir, it will not be 0 joule, because 0 joule, that means here it's gonna that means like temperature very low. But we say, for example, it will become 200 joules. The energy that as a thermal energy in it, it's gonna be, for example, what? 20 joules. That means here it lost 80 joules for warming the wall of the room, and that's the goal. In this case, how we count the efficiency? The efficiency we counted by 80 over the 100, not 20 over the 100. So it's going to be 80 over 100, because 80 is the goal. This is our goal. Our goal is for this energy. So usually the efficiency, we take the main goal, the quantity or the number that is given for that goal, based on what? On the input energy. So heat engine, we understand is it changes thermal energy into mechanical energy. Okay, last point now we are going to talk about is entropy. What is entropy? Entropy is a measure of how random the system is. So if I have a system here, system, that means like a material and objects or particles inside it. This system now, the measure of its randomness, it will equal the quantity of heat that this system has over the temperature of the system. And this temperature has to be in Kelvin. It has to be in Kelvin unit, not in Celsius. If it is in Celsius, you need to change it. So how to change from Celsius to Kelvin? By adding 273. So if I tell you now what is the boiling point of water, as we said, it's gonna be what? 100 Celsius. This is now Celsius. Okay, what is it in Kelvin? You're gonna add 273 to it, so that means it's gonna be 373 Kelvin. 370, yes, 2 Kelvin. So you change here the temperature. If it is given in Celsius, you change it into Kelvin, then you divide the amount of heat, divide by the one, you get the entropy of the system. That's for these points, and I hope you understand it. Thank you so much.